On January 28, 1986, Space Shuttle Challenger stood on Launch Pad 39B with 7 people aboard. The mission was familiar across the United States because teacher Krista Muckawliff was part of the crew. But before the countdown reached 0, engineers had already argued that the cold could keep a critical booster seal from working. This was not a minor maintenance note. The seals were classified as criticality 1. If the joint failed, the vehicle and crew could be lost, and there was no backup. The central question is not simply why a rubber ring failed. It is how an initial recommendation not to launch became approval, and what the first seconds after ignition revealed. Each solid rocket booster was assembled from large cylindrical segments. Where 2 segments met, a field joint had to contain rapidly rising pressure. 2 rubber O-rings sat inside the joint. The primary ring was expected to move into a sealing position. The second ring was intended to provide redundancy under limited conditions. Ignition did not leave the joint perfectly still. Pressure changed its shape and could open a small gap, a movement the investigation called joint rotation. The seal therefore had to respond quickly. At warmer temperatures, rubber recovered more readily. In deep cold, the O-ring could become slower and less resilient, giving hot gas time to pass before the seal reached the right surface. The danger was not newly invented on the night before Challenger. Earlier flights had shown O-ring erosion and hot gas blowby. After a secondary ring showed erosion on Mission 51B, a launch constraint was imposed and then repeatedly waived. The Rogers Commission later found that the seriousness of this history did not reach the highest readiness reviews in a clear form. The forecast for launch morning was far colder than any previous shuttle launch. On the afternoon of January 27, engineers at MOR Unquiet began reviewing what low temperature could do to the joints. Engineer Robert E. Bulling later recalled that predicted conditions were well below their experience and qualification data. During an evening teleconference, Unquiet engineers presented the concern to company and NASA managers. Their written recommendation was direct. Do not launch if the O-ring temperature was below 53 degrees Fahrenheit, the temperature of the coldest previous launch in their data. The forecast at the pad was much lower. The evidence behind that boundary was imperfect. Managers challenged whether the available flight data proved a precise temperature cutoff. That was a legitimate analytical question, but it changed the burden of proof. Instead of requiring evidence that the seals would work in an unprecedented cold, the discussion increasingly demanded proof that they would fail. The Unquiet managers asked for a private caucus. The company's position changed. A new recommendation supported launch, and the no-launch chart was not carried forward as the final position. Engineers including Roger Boy Jolie and Arnie Thompson continued to oppose launching in the cold, according to the commission record. The reversal did not mean every decision-maker now possessed the full history. The commission concluded that those who approved the launch were unaware of the contractor's initial written recommendation, the engineers' continuing opposition, and the extent of earlier O-ring problems. It called the launch decision flawed and based on incomplete and sometimes misleading information. The cold affected more than one component. Ice had formed around the pad, and Rockwell raised concerns about possible ice damage during launch. That concern also did not reach the final decision-makers with full clarity. The countdown was delayed, while an ice inspection team examined the vehicle and pad. At launch, the air temperature was about 36 degrees Fahrenheit. The right booster's aft field joint was colder. The commission estimated that parts of that joint could have been around 28 degrees, with uncertainty of several degrees. These conditions were far outside previous launch experience. At 11:38 Eastern Time, the boosters ignited. About 2/3 of a second later, cameras recorded the first puff of dark smoke from the right booster near the aft field joint. More puffs followed. The physical record showed that material meant to seal the joint was being burned and expelled almost immediately. Then the smoke stopped. That did not mean the joint had recovered normally. Investigators concluded that combustion products temporarily sealed the opening. For almost a minute, the vehicle continued climbing while the damaged joint held only because debris had formed a fragile barrier. Around 59 seconds after launch, a flame appeared from the right booster joint. The shuttle was entering the region of maximum aerodynamic pressure. The flame grew, impinged on nearby structures, and the failure sequence accelerated. At 73 seconds, the vehicle broke apart. This episode does not use that moment as spectacle. The relevant evidence is the chain that began before liftoff. The Rogers Commission identified the physical cause as a failure in the pressure seal of the right solid rocket booster's aft field joint. The design was unacceptably sensitive to temperature, dimensions, materials, assembly, inspection, and the effects of reuse. Cold weather made the seal response worse, but temperature alone was not the complete cause. The Commission also identified a contributing cause in the launch decision process. Safety information did not move cleanly through the organization. Serious anomalies had become accepted through repeated waivers. Engineering uncertainty was converted into permission to proceed, while the people with final authority did not receive the full argument against launch. That distinction matters. The engineers did not possess a perfect prediction of the accident. They had a warning grounded in prior erosion, seal behavior, and conditions outside the flight database. A responsible decision system should not require engineers to predict the exact failure before an untested condition is treated as dangerous. The redesign that followed changed the joint, added capture features and heaters, and tightened the rules around launch temperature and verification. The shuttle did not return to flight until September 1988, after the hardware and the management system had been examined. Challenger is often compressed into a phrase. Cold weather caused an O-ring to fail. The records show something more consequential. A known weak point met unprecedented cold, and the decision process stripped urgency from the warning as it moved upward. The physical seal failed during launch. The information seal had failed the night before. The lesson is not that managers should always accept the first objection, or that engineering data must be perfect. It is that uncertainty near a catastrophic boundary must be made visible, preserved, and resolved before a schedule becomes permission. If you prefer evidence over legend, the next case is already waiting in the archive.